All right, let's try again. I'm sorry. It's been a long day. It's in the evening as I'm recording this, and I'm a bit tired. Let's try this again. So we have our power allocation, which is given by this expression here for any SNR greater than the cutoff value and zero otherwise. And this cutoff value is to make sure that the average power, so the sum of the powers on average is equal to the average power constraint, like this, for 1 over the number of channels. Then on the figure, I show on the x-axis signal to noise ratio, gamma. On the y-axis will be related to the power. I can order the channels from left to right, so the ones with lower signal to noise ratio are bad channels, and with high signal to noise ratio are good channels. I then draw this function, p bar k 1 over gamma, so that's this function here. I also have one signal to noise ratio, which is the cutoff value, gamma k, and then if I evaluate the function I plot in this value gamma k, I obtain this value here, p bar over k times gamma k. This gives me then this horizontal line. And now the allocated power is the difference between this horizontal line and this curve, right? That's exactly the power that I will allocate, this value here. And now what we see is that when the SNR is high for a very good channel, the difference between this horizontal line and this lower curve is very high, which means I will allocate a lot of power. As the SNR gets worse and I go towards worse and worse channels, the amount of power I allocate will be low. At some point, I go below my cutoff value and I don't allocate anything anymore. And now this cutoff value, gamma k, I can move it to the left or to the right. And what happens then? If I move it to the left, then this value will go up. And then this horizontal line will also go up, which means I'm increasing my water level. And that then means that the total power I will allocate will also increase. Right, this will be my new P of gamma. And that means that in total I have more power to allocate. So that means that I will have a higher average power. So here I will have an average power P bar 1. If I shift my gamma k to the left, then I will have an average power P bar 2, which is greater than P bar 1. So this allows you to modify gamma k moving into the left or to the right, which moves your water level up or down to meet the total power constraint that you have. But given the gamma k, you have a closed form expression of p. And of course, given p, you have a closed form expression of m. Now, as I said, the way that we solve the problem leads us to this modulation format selection, right? M of gamma is gamma over gamma k. So we recall that these were the solutions. So this is the expression for the modulation format as a function of the power allocation. And this was the power allocation. If I substitute all of this back, I get this expression. So how do we do this in practice? How do we solve this problem in practice when the M can only be discrete? So suppose that we have certain discrete levels M, 2, 4, and 8, so BPSK, QPSK, and 8PSK, for instance. We then solve the following problem. We first make a guess of the water level. We choose a gamma k star. Given this gamma k star, we immediately find M, right, from this expression. Given this value of M, we then immediately find the power allocation, right, which follows from this expression here. Given this power allocation, we can then compute the rate from the objective function. And then we vary this value gamma k star. So we move this gamma k star left or right, higher and lower. If for each of them evaluate the rate, which in turn depends on the power and the modulation format, and then we just pick the gamma k star that maximizes this rate. And then you will have something that looks like this. So for gamma k over k star less than 2, I don't send anything. Between 2 and 4, I will send something. And the amount of power that I will allocate will reduce with more power, with more SNR. That's what this also shows. So I pick a certain M, And then the power I allocate is inversely proportional to the SNR. So for low SNR, I will allocate lots of power and then it decreases because I only need to support BPSK for a certain performance. At some point, I will switch when gamma over gamma k becomes 4, and I start again with high power and I reduce, and at some point I will switch to 8. And I basically change this gamma k star in order to totally optimize the total rate. And the figure on the right shows what then happens as a function of the average SNR, the total rate. In red is if you have continuous modulation format, and in blue if you have discrete modulation formats with a certain number of modulations available. Good, I think we have only one more topic. Yes, very good. What we've seen so far is statistical water filling. So this was what we've seen here, where we have an average power constraint. This means that over time, we need to make sure we don't spend more than our average power. We can allocate a lot of power now, but that means that later we cannot allocate so much power anymore because we've spent it. Deterministic water filling is a different problem where we have at each time a total power we want to allocate. So we have a total power to give, and we should always spend this total power, but we choose how we spend it and how we divide it over multiple parallel channels. So we have a scenario with n parallel channels, similar to like our diversity branches, but we want to now send independent data over these channels. For each of the channels, we know what is the gain of the channel. So let's say we know the envelope. That's the absolute value of the channel, the complex channel. We know the bandwidth and the noise. And we need to select power for each channel and a modulation format. And then we can again formulate this as an optimization problem of the same form as before. So we maximize, with respect to the transmission power, the sum of the rates over all the channels. Okay, so we have a sum, and here we have an expression of the rate, log 1 plus SNR. So this is a signal-to-noise ratio over the ith channel, the transmit power, the channel amplitude squared, and then the noise power. Okay, and I can write this as, again, as gamma I over P, where this is the total power, and by a suitable definition of gamma I. And we have a total power constraint P. So here, there is nothing random. I should stress this. Everything is deterministic. The channels are given to you. So this is very different from statistical water filling, where everything is random. You have only one channel, and you need to decide over time how much power to allocate, making sure you don't break the average power constraint. Here, there is nothing random. You just need to allocate power, and you have to meet the total power constraint. Now, the problem is exactly over the same form as before, and the solution turns out to be that the total power you allocate will be P times 1 over cutoff value minus 1 over an SNR, and this is chosen again to satisfy the total power constraint. And the mapping from the general formula to our case is given by these expressions here. So if you want, you can try to map this problem to the general formula, and then you will see that you will find this kind of solution. And now this also has this interpretation of water filling, which is what we have here. So now in the x-axis, instead of having SNR, we have the channel indices. So channels are just from 1 to n. On the y-axis, we have a measure of SNR of 1 over SNR. So this is 1 over SNR. This means that the good channels are here and the bad channels are here. And then we have this cutoff value 1 over gamma c. And then the power that we allocate is given by this difference between these two values. So the power we allocate is P times this difference of these two values. And we see that for channels that are very good, on the low side here, there's a big difference between 1 over gamma and the water level, so we allocate a lot of power. Some channels are worse, so we allocate less power, and some channels are above the water level and we allocate no power at all. As before, we can raise the water level or reduce the water level. When we raise the water level, we'll have another line like this, and that means we will use more total power. If on the other hand we reduce the water level, we could have, let's say, a curve like this. And in that case, we will have less total power. And the total power would just be related to this. So the control of this water level is a way for you to make sure that you meet the total power constraint. But given this gamma c, the problem has a closed form solution. Good. All right, this was a bit tough lecture, also for me. So this is what we learned today. We've seen why we want to do adaptive transmission. We also talked a little bit about benefits and drawbacks. So as drawback, we need, for instance, we need this channel state information. We need lots of assumption regarding the channel. You should be able to solve rate and power adaptation problems numerically, and you should also be able to derive and implement both statistical and deterministic water filling. So it's good to try to solve these problems yourself and play around with them. Good, this ends lecture 7, then I will see you soon for lecture 8.